Hello everyone, and welcome back to the channel. In today's video, we're deep diving into rational functions, what they are, how they behave, how to analyze and graph them like a pro. Whether you're cramming for an exam or just brushing up on your skills, this is your one-stop guide. Now before we start, make sure to check out the Gavilan Tutoring Center in Gavilan because it helps online resources such as mine to prepare students and help them. You could also reserve in-person tutoring or online tutoring if that is what you can do. So, let's get into it. Rational function is any function that can be written as the ratio of two polynomials, like this. Let's say we have f of x is equal to p of x over q of x. Now, p of x and q of x are both just polynomials. And a polynomial is a function that has two or more terms. So x squared plus 3 is a polynomial, x minus 3 is a polynomial. So this could be a rational function. Okay, the domain of a rational function is all real numbers except for when the denominator equals to 0. Why? Because division by 0 is undefined. You cannot do it. Trying to divide by 0 is like trying to microwave a spoon. So, how do you find the domain? Let's say this is our function, x squared plus 3x plus 2 over x minus 1. The domain here is all real numbers except for x equals to 1. Because when x equals 1, the denominator equals 0, and you can't have that. So, what are vertical asymptotes? Vertical asymptotes happen when the function goes all the way up to infinity or drops down to negative infinity. It's usually where the denominator is 0, but it doesn't cancel out. Like in this function, or let's say we have this other function. Like in this function, we have x squared plus 3x plus 2 over x minus 1. So if we were to graph this at x equals 1 on the graph, there would be this invisible vertical line that would stop a graph or a function from going through or passing through. So any function here would be forced to move around it, and it wouldn't be able to go through because at x equals 1, this function is undefined. Now let's move on to holes. And now I'm not talking about the one movie that Disney made, which was super good. I'm talking about holes in graphs. A hole in a graph appears when a factor cancels out from both the numerator and the denominator. This means that the function is undefined at that certain point, but there's no vertical asymptote. Think of it as just a missing dot on a graph. So let's say we have this. Let's say we have this function, x squared minus 1 over x minus 1. Now you might be thinking, okay, well, what can cancel out from here? Well, if you saw my previous factor video, you could factor this out to x plus 1 and x minus 1. This will stay as x minus 1. Now you see you can factor out the x minus 1 and the x minus 1, which means that at the point x equals to 1, there is a hole on the graph because the point there is undefined, but there is no asymptote. Now, we can move on to other forms of asymptotes. Horizontal and slant asymptotes describe the behavior of the graph as x goes to infinity or x goes to negative infinity, which means they're kind of like the limits. If the degree of the numerator, let's say we have a to the n over b to the m. So, if the degree of the numerator, n, is less than the degree of the denominator, the asymptote is at y equals 0. If the degrees are equal, you have to divide the leading coefficients to find out what the slant asymptote is. So let's say we have a function 2x squared plus 5 over x squared minus 3. You don't pay attention to these constants. You could just erase them. you focus on the 2x squared and x squared. So as x goes to infinity, these will both equally increase, except there's a 2 here. So if you cancel these x squareds out, you'll just be left with a 2. And a y equals 2 is equal to your horizontal asymptote. So here, you should say the coefficients. Now, if the degree of the numerator is no horizontal asymptote, and instead, there's just a vertical asymptote. So this is a vertical asymptote. Now, you have to remember this. If the degree of the numerator is exactly 1 more than the degree of the denominator, so let's say n equals to 1 plus m. If the degree of numerator is 1 more than the denominator, you divide the polynomial using long division to find the slant asymptotes. So let's say we have x squared plus 3x, right? And we decide to divide that by x plus 1. This would be x, then this would be minus x squared, then minus x, so that would be 2x left. Now we do minus 2. And this would be minus 2x. And you don't pay attention to this remainder that's left. So this x minus 2, this would be the equation of the slant asymptote. So in this function, in this rational function, x squared over 3x over x plus 1, let's say we have it looking like this. X minus 2 would be the slant asymptote, and the function would not be able to cross it. But if the degree was greater than 1, or if the difference in the degree was greater than 1, if n is equal to m plus 2, or if n is equal to n plus c, where c is any number greater than 1, then this would be an oblique asymptote. You call an OA. And all the oblique asymptote means is that when you use this long division, you would get a polynomial where the degree is higher than 1. So you could potentially have a graph where there are functions that look like this, and the asymptote looks like this. I think this is pretty cool, so this might kind of be your little catalyst to learning more about math. Now, let's talk about intercepts. So to get the y-intercept, you just plug in x equals 0 and solve for this f of 0, right? But to get the x-intercepts, let's say you have this function that you had before, x plus 1, x minus 1, x minus 1. Or let's say, okay, let's give you a brand new function. You have x plus 3, x minus 2, and so let's say you have x minus 4 and x plus 2. To find out the zeros in the function, you plug in the numerator after factoring everything out. You plug in the numerator, set equal to 0, and solve. And these will give you your x-intercepts. But if you do the same with your denominator after factoring everything out, these will give you your vertical asymptotes. Just remember, zeros on the top, x-intercepts. Zeros on the bottom, vertical asymptotes. As long as the solution isn't canceled by the denominator or the numerator. Now, to analyze the behavior near vertical asymptotes, just check values very slightly to the right and to the left of asymptotes. So, like in this function, we have x equals -2 and x equals 4 as our vertical asymptotes, because these are the zeros in our denominator. So to find the behavior near these asymptotes, just plug in to into the function values that are extremely close. So what my math teacher used to say is you just plug in, let's say 0.1 away from -2. So you use -1.9. Then you plug in -2.1. And then you go -1.8, -2.2. And this way you'll see the behavior around this -2. And you'll be able to do this without a calculator, which is pretty awesome, because that means you can solve this without even using any help from computers. Or not solve it, you could graph it without using help from computers. And you do the same, you do the same with this x equals 4. Plug in 4.1, 3.9, 4.2, 3.8. And it's pretty cool. So, just as a step-by-step rule, to graph rational functions, first, you find the domain. You find when it's equal to 0, you find what x values can exist. Second, you always factor and simplify. And this could also be your first step, because it will help you to understand what the domain is. So you factor, you use your domain. And then third, you identify any holes, right? You didn't find any holes, and you do this by seeing your factored out rational function and by canceling things out. Second, you identify your intercepts. Then you can identify your asymptotes. And all of these things, you don't have to follow this step by step. You could switch around. You can find your intercepts, then your holes, then your asymptotes. But it's just good to have a step-by-step kind of formula. Then 6, just analyze this end behavior, like I showed here, the ends. And then 7, to make it completely sure, you could plot some points. You could plug in some critical x values and plot some points to make it extra correct. But really, you could just sketch the curve, approximate the curve using this already given information. So, I hope you guys enjoyed this video. If you want more help, go to the Gavilan Writing Center website, like WConline, or visit the Gavilan Writing Center in person. Just pop in the library, say hello. I'm usually there, other people are there, and they can talk to you and help you out. And if you guys wanted to know what the significance of the thumbnail was, we could talk about that now. So, this thumbnail was really just me kind of playing around, trying to see how to make rationals more understandable. Next time, I'll try to make a thumbnail more related to the math concept. But here, we have a guy on top and a guy on the bottom, and it symbolizes a fraction. And that guy on top has a treasure chest with him, so that's like 2 terms. So that's a polynomial. And then the guy on bottom also has a treasure chest with him, so that's kind of like 2 terms. So it's just a polynomial on top and a polynomial on bottom, which is a rational function. And it's kind of funny because it looks like the guy or the polynomial on the bottom always has to hold the polynomial on top. So, if you enjoyed this video, leave a like, subscribe to the Gavilan YouTube channel, and check out more videos coming soon. Thank you.